For Unit 7 on Atomic, Nuclear and Particle Physics, we're going to start off with Topic 7.1 on Discrete Energy and Radioactivity. To begin with, though, I'll just mention here briefly, usually this sort of unit in a physics course, you go through a bit of a history of the development of understanding of the atom. That's not actually required for the IB, so we're just going to sort of jump right in. And so some of the foundational understanding that would underpin some of this stuff is kind of missing, but hopefully we'll be able to just pick it up as we go and make sense of what we need to make sense of. So when we're looking at this idea of energy levels, we first of all just need to make sure that everyone's aware that when we're dealing with atoms, we have the general structure that you should have seen already in some of your middle school science classes, and that is that an atom consists of a positively charged nucleus, and we'll see later in when we get onto radioactivity that the reason for the positive charge is due to the protons, and there are also neutrons there as well, but at the moment we're just worried about the nucleus itself, and surrounding that is some electrons, and those electrons are negatively charged. So the basic structure, that's what we need to start off with, and we're basically then looking at this model, say, of a nucleus, and then around that nucleus we would expect to find an electron. So that's our electron there, and that's the nucleus. Now, this is where we need to start to get a bit more specific about what's happening with this idea of energy levels, and where some of the background of looking at our development of understanding comes in handy. The idea here is that these electrons can't exist in just any orbit. So when we draw diagrams, we represent them, as you can see on the left here, with this dashed line, and that's because we have these electrons. We consider them to be orbiting. Now that model has some flaws in it, but we'll go with it because it generally sort of covers what we need to cover and make sense of the key properties. So those orbits don't exist at just any sort of radius around the nucleus. They exist only in specific orbits, and those orbits have a certain amount of energy associated with them. Sorry, using the same word twice. And that's where we get the term energy levels. So in this particular case, I've drawn one particular energy level, so that would be n equals 1, but then somewhere a bit further out we'd have another energy level that would be represented by n equals 2. We could then go out to n equals 3 and 4 and so on, but just for the purpose of this diagram I'll just leave it at n equals 2. Now, what determines those energies we're not going to cover here. It will get covered in Unit 12, which is an HL topic, but ultimately here we just need to be aware of the fact that electrons exist in certain orbits that have very specific amounts of energy. Now, before we go any further, we're just going to mention here that hydrogen is the simplest element to deal with. So the reason for that is that it has just one proton in the nucleus and one electron orbiting that proton. So that's the simplest atom to analyze. And so that's where we're going to start. And we won't really progress any further than that, given that when you start to look at multiple protons and multiple electrons, situation becomes far more involved, so we'll just start with hydrogen and have a look at the basics in that sense. Now, with hydrogen, the electron or electrons in hydrogen atoms are usually found in the ground state. Now, by ground state, what we mean is that they are as close as they can possibly get to the nucleus, so they're held in as tightly as possible, and that corresponds to the energy level n equals 1. So on that diagram above the closest energy level. But they can jump, and when I say jump, we're using that word in a slightly, it doesn't really explain what's happening here all that well, but it's an easy term to use to explain what's happening when an electron moves to a higher energy level. We've said that the electrons can't exist between energy levels, they have to exist only in the given energy levels, so jumping between them is not the best word to use, but it's terminology that's fairly easy to wrap your mind around. So the electrons can jump to those higher energy levels when the atom is energized. So in that example above, we could see that the electron might jump from n equals 1 to n equals 2 when it becomes energized. We'll talk about what energizes an atom a little bit later, but that means then that we need to consider what all of the possible energies are. So if we look at energy levels for hydrogen, so we'll have the energy level given by the value n, and the associated energy with that energy level as well, and we'll use electron volts here as the unit to state what the corresponding energy is. So we'll go down to the 5th energy level. Note that that would continue on up to infinity, but we're only going to consider the first few, because once you start to get a little bit higher up in energy levels, the values get so close together that there's very little difference between them realistically. So if we just go through, this is not something you need to calculate. This is just some given values here, and you'll notice the values are all negative. So that means eventually they're getting closer to 0, and that means then when we get to when n is equal to infinity, that would correspond to 0 electron volts. Now that idea of 0 electron volts, that basically means that it's when the electron is not attached to the atom. So this, when you've got an electron that gets out to infinity, you're basically ionizing the atom. So that's known as the ionization. You'll notice that if that's 0 and an electron is in the ground state of negative 13.58, then you need to energize it with negative 13.58 electron volts in order for the electron to be ionized from the atom itself. We can now translate that into an energy level diagram, and basically it's just making it easier to look at the transitions between the energy levels and represent those energy levels themselves. And the diagram looks like that one there. You'll notice that we've got on the right hand side we've got the energy level value, so n equals 1, and you can see as we go up to 2, then 3, 4, 5. Notice that we've got a few more added in this region here, but ultimately they increase significantly until we get up to the this one at the top here, which is n tending towards infinity. On the left hand side we have the energies associated with those energy levels, so you can see negative 13.58 down the bottom, and then going up to negative 3.39 and higher above that. Think of those values as being how much work needs to be done to get closer to ionization. Keep in mind here also that this is just hydrogen. There are different energy level diagrams for every element, but we'll only be dealing with hydrogen, as I said. And the other thing that's important here is not just the energy levels themselves, it's the transitions between those energy levels. We'll have a look at that in more detail in the next video.